Hello everyone, my name is Maki. I come from Airwallex, and it is a pleasure for me to attend and speak at this conference. My topic here today is interactive business process with Temporal. This topic actually comes from a project we launched in Airwallex a year ago. At that time, we had a lot of endless conversations about system designs with Temporal, and among all the topics being covered, the interactions with people being the most challenging. So I got the idea that challenges and the solutions we have encountered may be worth sharing, so I've come up with this lecture. And the first word I want to explain is what is interaction or interactive. This means that there are people engaging in the process. They read from the process, and more importantly, they send write requests to the process to move it forward. And users involved in this kind of process usually expect instantaneous responses after their interaction thread. And generally speaking, transfers are the most common use case of Temporal. Typically is not a process of this kind. Transfers usually proceed automatically to completion once started. However, such a process can evolve to be interactive. Just imagine what if managerial approval is required before a transfer can proceed, and this will make the whole process interactive. And we will use the transfer approval process as our case of analysis, so that our lecture will not be too abstract and theoretical. The next keyword is integration. This means we will focus on how to combine the interaction with Temporal. We will not talk about business features that are not directly related to Temporal, and I will not explain the basic knowledge of Temporal either. I know you're all very familiar with it. I assume we all have the basic knowledge of the programming model of Temporal, the primitives like workflows, activities, signals, and queries. And I also assume we understand the architecture of the Temporal system, the three basic roles, so Temporal Cloud, Temporal Workers, and external Temporal clients to start workflows and send signals. The only concept I want to explain is the workflow local context, because I invented it myself. Local context refers to all the local variables inside the workflow definition. Here is an example of local context. It is written in Kotlin because Airwallex uses Kotlin a lot. It is a simple string in the workflow definition because this is a simple workflow. But in a very complicated business workflow, the local context can compose a group of composite data structures. And Temporal blesses us with the convenience to store data directly in the local context and query directly from it. But sometimes it is so convenient that engineers abuse it easily in our program thread. We will refer to this term a lot later in our lecture, and please keep it in mind. Now, without further ado, let's get started with our adventure. This is an example. The transfer approval process starts with a user requesting some transfer in our system, let's say $5,000 from account Alex to account Bob. And the system then recognizes it as a substantial amount and requires a managerial approval before it can proceed. Then probably an email or some text message is sent to the only one manager of the requester about this transfer. But after a while, no one responds, and the system sends a reminder email again. This time, this manager comes and approves it. Now the transfer is moved forward and is made. To get a task solution for this process, we first need abstraction. And we use a straightforward way of mapping directly the business features to the temporal concepts. In this way, the whole business process becomes workflow. And the steps inside the business process, like sending emails, starting an approval task, making transfers, become activities. And for the email reminder, we have the favorite, everyone's favorite, long wait. And finally, for the human interaction, we have signals to send managerial approvals from external clients. So far, everything looks very simple, right? The next is to build bricks for our architecture. Undoubtedly, temporal workers and temporal cloud should be in the picture in the first place. And we also add a relational database to store our business data. What's notable here is I also add RPC service as an adapter layer. This provides convenience to other domain applications that don't want to integrate with us with temporal client. They only want to just have RPC calls. And I want to explain a little bit here that RPC service has a temporal client inside it. It doesn't communicate directly with our workers. It sends requests to the cloud where our workers pull messages. And the cloud is a durable bridge between the two applications. So far, we have the overview of our architecture. And the process actually starts with a user making a transfer from a web page or mobile application. This kind of request actually has a unique transfer key for idempotency. And product features, UI designs, and front-end engineers work together to make sure the user doesn't start two transfers mistakenly with different keys. Now, at the backend, we need features to achieve exactly once and idempotency. What's your problem?
No, you're good. Keep going.
Okay. And with temporal, everything will be quite effortless, right? We can just use the workflow, a transfer key as a workflow ID, and temporal will guarantee we will now start two running workflows with the same transfer key. It will just return errors to our Stack Overflow requests. And with this analysis, the first implementation will be quite simple. We just start a workflow execution in our RPC handler. And if we get no errors back from the temporal cloud, we are sure it is durable there, and the transfer will get executed. And at this time, we can just inform the user that their transfer has commenced. The next two steps are quite straightforward, actually. The first is we start an approval task for the manager and send an email afterwards. The only thing we need to worry is the consistency between the two steps, that we always want the manager receives an email after the task is created, is assigned for him. And this implementation is typical use case of temporal, that we start two activities, one for each task respectively. And the failure policies and the retries of temporal will guarantee the execution of two activities, even in the face of network glitches or something like this. Now we have reached a point that our workflow needs to wait. We have two waiting conditions. The first condition is that we need to wait for the manager to interaction. The second wait condition is some 24-hour timer that if no one shows up, we need to remind somebody. This feature will be my least favorite if we had not used temporal, because I must use some extra cron jobs or queuing systems that support delayed messages. But with temporal, it will be very straightforward. I have put a call snippet of Kotlin here to show the simplicity. To wait for the manager's request, we just create a local variable. That is our local context. And to have a signal handler to store the manager's request into it. And we just need to wait for the signal. And for the remainder of 24 hours, the workflow await happens to have a timeout. And it also has a Boolean value to tell us if the workflow resumed from a timeout or from our business condition. So we can see from this example, the implementation of waiting with temporal is really simple. I only have no more than 10 lines, I guess. Our journey thus far has been remarkably smooth. We have successfully implemented most of our steps, leveraging tools offered by temporal. The only step left is all about interaction with our manager. And let's first get a simple solution that immediately comes to mind. The interaction actually involves several steps. The first is the manager views the contents of the transfer. Since we have stored everything in the database, we can just query directly from the database. Then the manager needs to make a decision based on the information. Let's say he wants to approve it. The decision will be sent through a signal handler to the temporal cloud. And as soon as the signal is accepted by the cloud, we are very sure the signal will be stored durably at the cloud side, and we can, at this time, we can respond to the user that your approval is successful. And on the other side of the picture, that is inside the workflow workers, the workers, upon receiving the approval action, our waiting condition used to be blocked, resumes. And the workflow worker starts an activity to update the status of the database. And finally, a transfer will be made. I don't want to talk too much about transfer because Temporal has already provided a lot of examples in this use case. Right now, this is a viable solution for our interaction process. But the questions arise immediately after we have designed it. The first question is, when a manager comes to approve the transfer, should we update the database directly instead of sending requests to the temporal cloud? It was actually a very popular question when we first shared our design with our team. And when engineers noticed we bypassed the database and wrote to the temporal cloud. This question was actually reasonable because if we had not used temporal, we would have updated database directly in our RPC handler. And this is common practice with traditional architecture, right? But with temporal, we have workflows and a new name, durable executions. And durable executions by name are durably stateful. So we can update directly in our RPC service for the database. But even in this way, we still need to notify our workflows, our durable executions about the progress. We need to guarantee the two are consistent. We cannot achieve consistency with two simple calls in our RPC handler because there are always annoying edge cases that the requests sent to temporal fail after the commitment of the database. And this kind of inconsistency is usually the very reason we include temporal in our software stack in the first place, and we don't want to say it create more of it instead of solving them. Before we rush to our first conclusion, I want to explain a bit more about the reason behind this question. I think engineers are very meticulous with consistency between different data storages. And we don't even have the thing of orchestration consistency because orchestration most of the time are stateless. And we don't have consistency for stateless things. But with temporal, our code becomes literally durably stateful. And this is a new learning, and we sometimes forget this new learning somewhere in our program, and then we end up with mistakes. To solve a problem of this type, we can build a rule of thumb to divide the responsibilities between RPC service and temporal worker. And we can refer to this rule of thumb when we do designing and coding work. So this rule of thumb is our first takeaway, that the responsibility of temporal is single source of state changes, because temporal is designed to maintain consistency. And for the RPC service, we use it as an adapt layer for workflows and a read-only access layer to the database. This is our first takeaway. Our second question now comes to the second question. Our second question arises when more than one manager has authority to approve the transfer. This actually creates a concern of data racing because they may come to interact with our system at the same time. In the face of multiple managers, for example, one manager sends approval and the other's rejection, our system still wants to respond with fresh status of transfer after their interactions. We want to respond something like this. One manager will say, the transfer is approved by you successfully. And others will say, whoops, the transfer has been approved by someone else. However, our current system design doesn't support this feature right now. Actually, two reasons give rise to this incapability. First, in the RPC handler, we only send signals and we never care about responses. And when multiple signals come into the picture, we don't know which one is accepted by the logic inside our workflow executions. And the second reason is at the worker side. We just dumbly store the request in the local context, and we never take efforts and time to think if everything remains correct when we have different signals, and different signals can flow into the workflow in one batch. Now let's fix the two problems together. And we start with the worker side. Let's first decide a rule to accept different signals. We have a simple rule here that when multiple managers come to interact with our system, we accept the first one that arrives as a worker and drop the others. According to this rule, I adapt our simple happy signal handler by checking if the signal is a first. However, when I was writing the code, I was actually a little nervous at that time. I was wondering what if there are multiple threads for different signals trying to access and write the local context at the same time. And I was wondering if I need to add extra synchronization like logs to keep away from data raising. The good news is Temporal SDK solves the problem out of box for us. For the same workflow, our SDKs provides concurrency support, but they don't provide parallelism. This concurrency is deterministic, cooperative, multitasking, that is the coroutine model. And definitely, different SDKs map to different underlying language runtime. But we don't need to know much about this. If you are very curious about the SDK internal code, you can talk to Chad. And we only need to know how our signals will execute. Although they can be handled by different coroutines, at one time there's only one signal being handled. And the coroutine of this signal will not get stopped until it blocks. Since you have noticed, I put no blocking code in my signal handler, like some activities. So one signal will run to completion and the next one starts. So this is safe. Now we have finished with the worker side. Now let's move to our RPC handler. And to give accurate and instant feedback to managers, even though signals have no responses, we have workarounds and we all know we have queries. So we can just add a query in our worker to get the data in the local context and return it to the RPC handler. I've also provided a simple code snippet here and to show you how effortless it is. What's nuanced here in this solution is that we actually create a happens before relation of signal and query in the RPC handler. And the happens before relation will be kept within the execution of workers in the execution of workflow as well. So the query will not get executed until the completion of signal. And this point is very important in the success of this solution. With this new model, we will feel very relieved when multiple approvers come into the scene. Signals and queries of different approvers can mix, and they can arrive as a worker within one batch or different batches. But we are always able to pin down the first signal deterministically, and we can always query the correct result to our managers. Before we sum up our second takeaway, I want to introduce a new solution here, that is the temporal update. We came up with our project last year when we only had signals and queries at hand. But now Temporal has already provided a fantastic feature that combines both of them. And with the new update feature, we only need one RPC call from the RPC service, and we just wait for the synchronous response. And for the worker side, it is actually very straightforward for the refactoring. I just add a return value to our dear good old signal handler and transfer it to a new fancy update. Obviously, temporal update is much more convenient and straightforward. It doesn't require you to have a clear understanding of the nuance that happens before relation. That is execution order within the temporal workflow worker. But it is indeed a very new feature. As you can see, I still cannot import it from the 19th SDK I'm using right now. You need to start with 20. So this is the first takeaway of the second topic. We have two patterns of synchronous updates with temporal. And we'll stick to the second pattern, that is the temporal update, for the next topic. The final discussion comes from the common case that after a manager approves the transfer, we probably will read the transfer again. At this moment, the last thing we want for them is to see outdated information and get confused. This new requirement makes us question whether we are providing consistent user experience. If not, how can we make things better? Unfortunately, our previous design may surprise our users with inconsistent data. Because we split our reads and writes to different data sources. When we update the status of the transfer, we update the local context of the workflows. But when we display the information, we query from the database. And we even have some activity here to replicate data from local context to the database in an asynchronous way. With this design, if we read before the replication completes, we will provide still data for our users. In most cases, this is okay because the replication lag is usually tiny and not observable. But what if the read and write operations are performed by the same user? They will get surprised. And this type of problem is also known as read or write inconsistency. So now let's work on this problem. If we take different perspectives of our system, we get different interpretations of our, if we have different perspectives of our architecture, we have different interpretations of our problems. And we have different solutions, and different solutions have different advantages and disadvantages. The first perspective is to view temporal as kind of data storage, kind of source of truth. And in this view, that temporal forms a data cluster together with our relational database. In this way, the problem becomes observable data replication lag on certain read requests. And if we view the problem in this way, we actually come to a comfort zone because it is a typical problem with most database clusters. Here, we are dealing with a MySQL cluster comprising a single leader and two read replicas. To ensure read or write consistency in such a cluster, there is a common approach that if there's a possibility that the reads come from users that may just try to change the data, we can just read from the leader. And otherwise, we read from the follower. There are different ways to help us decide if the possibility exists. And in our specific case, reads from the managers, the people with managerial authorization, are the possible ones that suffer this kind of inconsistency. Consequently, their reads shall go directly to the leader. And returning to our cluster of temporal and relational database, right now temporal service as the leader and database as a follower. Drawing inspiration from our previous experience with MySQL cluster, we apply a similar approach. All managers now read directly from the local context of the temporal workflows. With this solution in our updated design, both reading and writing by managers come to the local context. And this ensures read or write consistency even in the presence of replication lag. However, before we celebrate this solution too eagerly, it's essential to exercise caution and scrutinize it more closely. What are the problems of this approach? I'm going directly to the answers. The first problem is the solution requires maintaining business data within the local context. While this may not sounds like a severe problem for simple systems like the one we discussed in this lecture, it becomes critical gradually with the involvement of our system. When more advanced features are incorporated, volumes and data, types of data we need to query from the local context grow. In an extreme case, we may end up building the entire database in the local context, just to obtain read-write consistency. Sounds like a very bad investment. The second problem is that Temporal isn't designed for flexible queries, whereas databases are. Many queries that are easily handled by the databases are not convenient with Temporal. For example, queries without workflow IDs, like performing a batch query across multiple workflows, are quite challenging with Temporal. So the solution may limit our ability of complex systems, but it is still a very handy solution for small and simple ones. Now let's explore an alternative perspective to enhance our quest for read-write consistency. Instead of perceiving Temporal as a source of truth, we can view it exclusively as an orchestrator. In practical terms, this means we shift away from local context as source of truth for business states, but we can still return orchestration-related flags within the local context. The new perspective offers an ultimate solution to replication lag. Because there's only one storage in the architecture, there's no replication, so we have no replication lag. And so the read-write inconsistency caused by replication lag vanishes as well. Now the problem comes to a practical implementation solution. We need to change our workflow definition because we used to update data in the local context a lot, like all the time. And we shall store things right now in the database. And we still need to keep Temporal as single source of state changes. There's actually a lot of pitfalls in the implementation. The first warning is we cannot add DB manipulations in signals and updates because they are workflow code, and workflow code will get replayed. To solve this problem, we can wrap the database manipulations into activities inside the update handler, so that the execution will be recorded in workflow history and will not get executed again in replay. And we need to make sure the activity is idempotent. With this solution, we can ensure that once the approver completes the update operation, the database is refreshed, and we are enabled to perform subsequent reads directly to the database. But the nuanced part here is the concurrent execution of multiple updates with this new solution. And because right now we have the blocking activities inside our update, and the sequence and the analysis of the coroutine model is quite different right now. This is a relatively harder part of this lecture, and I'm going to keep it out of today's speech. If you are very interested in the analysis of activities within updates in the time of concurrency, you can just talk to me directly after this talk. And things will be much more nuanced if we stay with the signal and query solution, because right now we have two temporal handlers to coordinate at one time. Now we have devised our second solution to achieve read-write consistency. With this solution, we only need one set of data models in MySQL, and we are free to leverage the powerful query capabilities of the database. And I personally really like the second solution right now, and we are migrating from the first solution to the second one. The final part is about a wrap-up of this lecture. We have three takeaways right now. The first is use Temporal as single source of state changes. It is about orchestration. The second is we have learned two patterns of updates. They are both synchronous and safe in the time in the phase of concurrency. And the third is we have learned two patterns of architecture design to achieve read-write consistency, and they apply to systems of different complexity levels. Here we are. This is so much for today's lecture, and thanks everybody for joining me here.